Okay, all right. So, yeah, welcome back from your break. So what we're going to do now, so we're going to continue our discussion. And what I'm going to show you explicitly is what happens for a 50-50 beam splitter. And we're just going to see basically that it does a pi-half rotation. Okay, so we're just going to see this explicitly. And like I said, it is important it's important to notice that the quantum version the quantum beam splitter gives rotations. So if we take, let's say, for example, we take a 50-50 beam splitter. We're going to see that this gives us a pi-half pulse, the equivalent of a pi-half pulse. So again, we have the incoming field A, incoming field B, output field B prime and A prime, where B prime for a 50-50 beam splitter is going to be B minus A over square root of 2. All I did is apply the formula that we wrote before with phi equals 0. And B plus A over square root of 2. Now there's something arbitrary about this choice of putting the minus over here. You can also put the minus over here. It's a completely arbitrary choice. In books, and you'll see this if you open Nielsen and Chuang, for example, this whole device for a 50-50 beam splitter is marked in this way. So the sign for this 50-50 beam splitter is this shape over here, where it has a dot on one side. And the dot is just to break the symmetry of the choice. So this is A and B incoming, and this is A prime. Sorry, in the way I marked it, it's B prime and A prime. And this is B minus A over square root of 2 and B plus A over square root of 2. Okay, so the dot here symbolizes where you would put the minus. And so what this construction shows us is that using two beam splitters, we can do a Ramsey experiment. A Ramsey experiment is a simple interferometry experiment where we're looking at phase accumulation. Remember, this is the equivalent of the free induction decay in NMR. If you remember, in NMR, you start with a magnetization, let's say aligned, and then what do? We apply a pi-half pulse. And if we're slightly detuned from the frame, what happens to the magnetization? It rotates. The frequency of rotation is exactly the detuning from our frame. Okay, so that is the phase accumulation. And we see these oscillations, and the oscillations will decay. And the decay is caused due to the finite coherence of the two states of the qubit. Okay? The same thing we can do in optics. Okay? So we can measure the T2 of our photonic qubit in this way. Okay, so Ramsey experiment. For measuring the coherence times of this qubit, you need to use two beam splitters. The first beam splitter our qubit comes into, this is A and B. Then we have an output mode. This is B prime. This is A prime. Then we place two mirrors. M. Two mirrors. So this mirror will refract, so we'll get minus B prime. And here we'll get minus A prime. Now for A, what we're going to do is we're going to add a phase shifter. The phase shifter is the equivalent of being off resonant in the NMR setup. This phase shifter will give us minus A prime e to the I phi. And then this goes into another beam splitter, another 50-50 beam splitter, which will then go this way and that way. And here we will put a detector, so we'll have a photon counter. Call this dA, and over here, photon counter dB. So it's going to be counting the photons.
A little unclear what you're writing right at the bottom.
Okay, maybe I'll erase this and write it all bigger. I'll redraw this again. Redraw it bigger. Yeah. Here, bigger. So we have, this is the first beam splitter, A, B. The output here is B prime. Output here is A prime. Here we have a mirror. Here we have another mirror. The mirror here will reflect this field, so this will be minus B prime. The mirror is just a beam splitter that is fully opaque, so it'll just give us a minus sign. Here we will get minus A prime, but we're adding here on the path a phase shifter, phi. So it's going to phase shift A by phi. So we're going to get A prime minus A prime e to the I phi. And finally, this is all going to come into another beam splitter. And whatever is transmitted here will go into detector A, and whatever is transmitted here will go into detector B. And this detector is just going to count, is there a photon and is there not a photon? Now, in the NMR setup, basically we were looking at the magnetization signal as function of time.
It looks like interferometer.
It is an interferometer. It is exactly an interferometer. Okay, this is why it's written that way. An interferometer is actually like taking your qubit, doing a pi half pulse, right? This is the equation that I'm trying to do. It's taking your qubit, you do a pi half pulse. Now you wait for a time. This is your time here, and you do another pi half pulse. If there's no phase accumulation, nothing happens. But if you do your pi half pulse, move away from the frame, just like in NMR if you would do slightly off resonant pulse, you would get a phase accumulation. This phase accumulation is as function of time, but here we did it as function of some phi. So suppose that we can control this phi. Okay, so, and after a certain time, you do another pi half pulse, and you measure the probability to be in your 0 state or your 1 state. You do that by repeating the measurement many times and taking the average. In an NMR setup, if you remember, you just do your first pi half. It accumulates phase, okay? But you're also measuring it, in a sense, okay? So you're basically, because you're already looking at the average there, so you're already looking at this decay. But it's effectively the same measurement. Okay? But except for NMR, all systems, atomic systems, superconductivity, the setup is going to be more similar in a sense to this. You would take your qubit, you would apply this pi half pulse, you would accumulate somehow a phase. Okay? Typically it's an artificial phase, so here you would put this and change this every time in order to see oscillations. It shows you that this is a coherent system. And then, once you're done accumulating a phase, you do another pi half pulse to project it backwards. Okay? So if you do a pi half pulse, you wait 0 time and you do another pi half pulse, you've inverted the population. Okay? So you start off, let's plot this. Okay, so this is a function of phase. And phase is how much time I wait in an NMR system or in any other qubit system. And here the phase is what material I put. And here I'm plotting the probability, let's say, to be in the ground state of the qubit. So when the phase is 0, so you do your pi half over here, the phase is 0. Okay, so there's no phase accumulation. You do another pi half. And then your probability to be in the ground state is 0 over here. Okay. Now we do the experiment again. We do a pi half. We accumulate a little bit of phase. And then we do another pi half. Now, my pi half takes me all the way down here. So it's not quite in the ground state. It's closer. So there's some chance I will get an excited state. Okay, so my probability is going to be something here. And you repeat this experiment many, many times, and you get an average value. And you keep doing this for many values of the phase, and you get these oscillations. And these are the Ramsey fringes. Now, if you have dephasing, some process where your phase is getting lost, random kicks to the phase, then these oscillations are going to decay. So you're going to have these decaying oscillations. And the envelope of these decaying oscillations, this is what we call T2. It is the coherence of your qubit. And as you remember, the two most important parameters for qubits, the two coherence times for a qubit are T1, that's the energy relaxation, and T2, this is your phase coherence. Energy relaxation, you don't need a beam splitter to measure. You just you start your system in excited, you wait to see when it decays to ground. And you do this as function of time. Now note here that I gave here time, and this is phi. So this is tricky. This really doesn't give us proper coherence times for this qubit. Okay, but the two experiments are related. And this experiment just gives us the Ramsey fringes. Is that... Any questions about this? No? We're good? We understand how a beam splitter just gives us rotations around the Bloch sphere? That's the important takeaway message. Okay? So now that we have a phase shifter and we have a beam splitter, we have full control over a single photonic qubit. Now what we're going to discuss is how do we interact two photons. Now interacting two photons is very hard. Light doesn't like to talk with light. It needs to do it through some mediator, through some medium. We're not going to discuss the physics of these mediums and nonlinear optics. There's a whole course on nonlinear optics. If you're interested in that, you should take that. But I'm going to give a simple model and just show you what it does and show you how it can interact photons, and then discuss how it is the largest bottleneck, or basically what kills this model for quantum computation. Okay, so this is what we're going to do next. Okay, so two qubit gates. Like I said, for two qubit gates, we need to use some nonlinear medium. And I'll explain what that is just now. So in linear optics, we know that P is just epsilon naught chi E, where E is the electric field. And this thing over here, this is called in general the polarization tensor. And for linear optics, this is just can be just a simple number. But if we have nonlinear optics, then we have dependence on higher orders of the field. Okay? So this thing here is just going to be some epsilon naught chi 1 E plus some chi 2 E squared plus chi 3 E to the third plus 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 and so on. This is the nonlinear response of a medium. Now what happens typically in materials, in real materials, is that this term drops due to symmetry. Doesn't have to be the case, but in a lot of real materials, this is what happens. And then we're left with something that looks like this. Epsilon naught chi 1 plus chi 3 E squared E. And the description of this thing, this is what you usually call a Kerr medium. Okay. Kerr refers to the degree of nonlinearity that you have. So opticians might refer to chi 3, chi 4 nonlinearity, and so on and so on. The simplest material and the most commonly found is, and the one that usually is, so if you read Kerr medium, this is typically what is referred to. Okay. And I wrote it in this way because here you have E squared. And E squared is the intensity of your beam. And it's simple to see that now, basically, your light, when it's traveling in such a medium, then your refractive index is going to be proportional to the intensity. I is the intensity, which is basically E squared. Okay, your electric field squared, that's your intensity. And now your refractive medium is just going to be some n plus some n2, this is a small factor, times I. Where I, let's write this explicitly, is the intensity. And I'm not going to do it on the board, but you can open up Wikipedia, and it has a nice simple derivation of this thing. So, Wikipedia is quite nice for many things. And so I is the intensity, and given in units of watt per centimeter squared, can give you some values. So for glass, N2 is going to be on the order of 10 to the minus 14 up to 10 to the minus 7 centimeters squared per watt. And for semiconductors, N2 is much larger. It goes from 10 to the minus 10 all the way to 100. And these numbers are also taken from the Nielsen and Chuang book where he has this discussion. I copied the number from there. So this is the concept of this nonlinear medium. And what we're going to do now is I'm basically going to write the quantum description of this nonlinear medium, just like we did for the beam splitter. I'm going to do for this nonlinear medium, I'm going to write the quantum description. And in the same way that you can show that the beam splitter, the quantum description of the beam splitter gave us the same behavior for a classical field, you can do the same trick here for this nonlinear medium. Apply it to a coherent state, a number state, and then play around with that and see that you get the expected behavior. Okay? So I'm going to write the quantum version of this, and then we're going to look at the quantum evolution, and we're going to see how that creates interaction between two of these photonic qubits, and then we'll discuss why this is actually a terrible idea. But before being a terrible idea, let's see how much of a good idea this is. Okay, so for a crystal of length L, so we have some nonlinear crystal of length L. We can describe it. Maybe I'll write the Hamiltonian first with time evolution, and then here, let me write the Hamiltonian and then I'll write for a crystal. So the Hamiltonian is just going to be some minus chi A dagger A B dagger B. This is the Hamiltonian. And then our operation K, using this Hamiltonian for some crystal of length L, is going to be e to the I chi L A dagger A, B dagger B. Note that you just need chi in the right units to make sense of this. Time, distance, it doesn't matter, okay? But here, L is given in, if chi is in frequency, then L will be in time. And what you can see here is that this evolution gives us, for a certain mode, it gives us a phase shift that depends on the occupation of the other mode. So if I know that the other mode has one photon, then I get a certain phase shift on A. If I know that this mode has no photons, this mode gets no phase shift. Okay, so we have the result of this Hamiltonian, and you'll see this form come over and over again. Okay, it's like this dispersive interaction. that causes a phase shift that depends on A and B. An easy way to see this is if I take this Hamiltonian, I can take this Hamiltonian and rewrite it in a simple form. So here, let me make a little square and show this explicitly. So I'll write the Hamiltonian for two modes. So one mode is going to be, let's do h over h bar, omega a dagger a. This is omega a dagger a. This is one mode. And this is b dagger b. This is the other mode. But now I'm going to add this interaction Hamiltonian. And the way I can write this interaction Hamiltonian is I can replace, I can write this in a slightly different way. So I'm going to erase this and write it again. So I'm going to write here, instead of omega b, I'm going to write omega b minus chi, right? Hang on. A dagger A, B dagger B. Okay, so I just took we have harmonic oscillator 1, harmonic oscillator 2, and interaction Hamiltonian. I've just written them in a slightly different way. And what you can see here clearly is that you have harmonic oscillator A and harmonic oscillator B. Only the frequency of harmonic oscillator B depends upon, anyone?
The occupation of harmonic oscillator A.
Exactly. Now I can also write it in the other way, right? I can also write omega B, B dagger B, and then omega A minus chi, B dagger B, A dagger A. And then it looks like I have one harmonic oscillator and another harmonic oscillator whose frequency depends on the frequency of the other. But a small frequency shift, as you propagate it in time, is just a phase shift. Okay, so this is a simple way of seeing that this is a phase shifting interaction between these two modes. And this is basically what is written over here.
Shay?
Yes.
Do we need to divide chi by h bar, or is the first Hamiltonian also
well, here I divided everything by h bar. So this is frequency, this is frequency, this is frequency.
Yeah, but the first Hamiltonian you wrote is...
yeah, here. Yeah, h bar. Sorry. My mistake, yes. H bar.
Okay, thanks.
Can you explain again what is K?
Okay, you can call it U. It's just a number. It's the unitary operation of the crystal. Okay, I just did e to the IHT.
Yes, okay.
Okay. But since the crystal is finite, so this T translates to some L, which is the length. Okay, but here L is given in time. So you have a crystal which is certain length, but you know the time propagation. So L is in time units.
So is this basically a controlled Z-gate?
Yes, it is exactly a control Z-gate. I'm going to write it now explicitly. Okay, so what we're going to do now is we're going to see how this is a CZ gate, basically. So if you operate K on the state 0, 0, or let's do this in a more compact way. So if I operate K on either 0, 0, 0, 1, or 1, 0, we will get the exact same states out. 0, 0, 0, 1, and 1, 0. If we operate K on the state 1, 1, then we get e to the I, sorry, not K, chi, e to the I chi L, 1, 1. And now we need to choose L or we need to choose such that the product chi times L is going to be, anyone?
Pi.
Pi, exactly, pi. And if we choose that to be pi, then we get minus 1, 1. Now remember, our qubits, this is not 2 qubits. This is a single qubit. We have a dual rail qubit. Okay? So let's see what happens on a dual rail qubit. Okay, because this needs to create interaction between 2 qubits. So we're going to have 4 modes in this operation. Okay, and here maybe I'll do it. Can I erase this? Yeah? Okay. All right. So let's erase this and do this over here. So for the dual rail qubit, our 0, 0 logical, we can choose our 0, 0 logical to be 1, 0, 0, 1. I'm inverting the 1 and 0 for the first qubit. Okay? 0, 1 logical is going to be 1, 0, 1, 0. The 1, 0 logical is going to be 0, 1, 0, 1. And the 1, 1 logical state is going to be 0, 1, 1, 0. Now if you take k, and now what we're going to do is we're going to apply k, and we're going to apply it on 2 middle qubits, 2 middle modes. Not on 2 middle qubits, 2 middle modes. So maybe I'll do a different color. So k is going to be applied on these here. Bad alignment, sorry. So this is what we're applying k on. And if you apply k on these, you can see that this stays the same. But if you apply k on this, then you get a minus sign. So you get minus which is basically minus 1, 1 logical state. And this is a C-phase operation between 2 dual rail qubits. Okay, so we basically have 2 minutes left. And so in these 2 minutes, I'd just like to complete the discussion of this photonic quantum computer and show you why this is really a no-go theorem, and you need more clever things in photonics to make a viable quantum computer. First of all, go read Nielsen and Chuang, the chapter on this. That's very good. But the biggest problem of using the scheme, and it goes to the biggest problem of using photons as qubits, it's the fact that they don't interact with each other well. And what happens is if you take photons and put them into this nonlinear medium, does anyone know what's the biggest problem? Anyone?
Energy.
Energy loss, exactly. There's a large loss. Because you need a large interaction with matter, this matter will cause loss. And for the very good conceivable single crystals like this, to get a significant operation, to get a pi, you would need to lose on the order of 100 photons. And this is too big of a losses to handle by any system. Okay? And this is the big problem for photonic systems. What the more advanced schemes for photonic systems do, whether it's the KLM model or the measurement-based model, is that they replace photon-photon interactions with other nonlinear operations. A quantum computer can have many linear operations, but it needs at least one, it needs some nonlinear interaction. Okay, you can't just have harmonic oscillators. You need the atoms. You need the two-level systems, okay? And you need to be able to control them. But it turns out that instead of doing the control on the qubits, you can just do linear operations on essentially classical states of light. Somebody mentioned polarization. But then leave the nonlinear operations to the measurements itself. So suppose that you do everything linearly but use photon number counters. That is a nonlinear operation. That can be replaced. Okay. Also, you can use other very specialized states to construct quantum computing. But the big thing that you need to understand from here is you need some nonlinear interaction, whether it comes in the control like we did in this model, or whether it comes in the preparation of the state, which we didn't talk about at all here. I just assumed that we can make single photons. This is a big problem on its own. Or it can also come in the detectors. Here, when I described to you, I told you, okay, we have a photon detector. It can detect 0 photon, 1 photon, or you can even have a photon counter that says how many photons that is. We didn't discuss the technology behind that, how feasible and how viable is that, but you can have your nonlinear operation either in the control or in the measurement, okay? Or in any component, basically. And this is those more advanced schemes that maybe at the end of the semester, if we have time, I'll talk a little bit about. And if we don't have time, someone can do it as a seminar, maybe, as an idea for a seminar. Are there any questions before we're done with photons? Okay, so if there are no more questions, what we're going to do next week is we're going to look. So far we looked at classical spins with classical light and quantum light. Then we looked and a quantum spin and classical light. Sorry. Then we looked at the quantum light. What we're going to do next week is we're going to look at a quantum two-level system interacting with quantum light. Okay, and this will give us the basis to discuss the superconducting qubits, the neutral atoms, the trapped ions, and cavity QED, the Rydberg atom space. Okay? All right. Well, thank you. See you next week.